All right, Bismillahirrahmanirrahim. Um, any questions before we begin? Okay, so we were discussing last time linear discriminant functions. We said there, broadly speaking, there are two approaches to learning discriminant functions in supervised learning. One is a generative approach, and we saw Bayes classifier as an example of that, and that actually involves estimation of a density function for each class. Histogram is an approximation for a density function, right? Or we said the second option is that we learn the discriminant function directly, and since we have imposed a restriction on the discriminant function, that the discriminant function would only be a straight line. Yeah, it's a only be a linear function. Line is in 2 dimensions, but in general it will be a hyperplane. So we looked at how we can learn that, and we so that problem just becomes learning the weights of the function while minimizing a cost. Okay, and so we saw an example of the cost function, which is really this function that I'm visualizing here, j of a. We saw example of that, and we saw how to optimize over it, and we saw gradient descent as a decent way to do that. Except for large data sets, you might want to prefer stochastic gradient descent rather than gradient descent, right? Okay, so now I want to talk just very briefly about the choice of the loss function or the cost function, and I will come back to this later when we talk about deep learning, inshallah. So the function that I said is misclassification error rate, right? So misclassification error rate would actually be flat in a whole region where the classifier does not change the label of any point. Okay, right? Because there is a whole solution region, so in that solution region the cost has the same value because no point, the label of any point is not changing in that region. Okay, now when I misclassify 1 point, I get this error. I misclassify 1 point, I get this error. If I misclassify 2 points, I get this error. I misclassify 3 points, I get this error. Okay, but over this whole region I'm misclassifying 1 point only. Over this whole region I'm not misclassifying any point, right? So what's the problem with this cost function? The problem with this is that this is a piecewise constant function. Your search is going to be guided by gradient, and the gradient is 0 here. If you were here, the gradient is 0. If you were here, the gradient is 0. If you were here, the gradient is 0, right? So when you start from a random point and the gradient is 0, well, gradient descent is not going to generate any improvement. It's going to say, well, the gradient is 0, right? So while this cost function makes very logical sense, I'm just going to count how many points are misclassified, but over a whole region the count is not going to change, right? Because the label of any point is not changing, so the count is not changing, and in that region then you're not going to get any reasonable gradient to follow, correct? So it's like, from gradient descent point of view, it's not a very good cost function. I could change it. I could find the squared error of A transpose Y, because that should really be, A transpose Y should really be 0 for a good solution. So I could use this squared error. How far away am I from a good solution? How far is my A from a good solution? Okay, and I could sum that over all my points. This sort of cost function will generate a more smoother error surface, which means gradient descent is supposed to work better. Or I could use this with what we call a margin. The margin says, okay, I have a solution region, all these A's are valid, but let's not choose a A which is too close to the boundary between being a good function and not being a good function, between correctly classifying all points or not correctly classifying all points. So there is a B added here, which is kind of like a buffer, a margin, that I don't want to be too close to the, I don't want a decision boundary that passes too close to the points when classifying them. Okay, yeah. Yeah. Yeah, actually that's a good question. I skipped a slight point here in writing these cost functions. So let me clarify that. Um, my pen is back because my original laptop is back. It got repaired. so, um, so basically, what the reason this cost function makes sense, it's actually a modified data set. What you do is, remember I drew this figure last time, that let's say these 2 points are one category and these 2 points are another category. Okay, and so any separating hyperplane passing through 0, because now I have the augmented vector, so passing through origin, but anything that passes between these is a good solution. Okay, in fact, for the normal vector we said there is a whole region of solutions because this plane can tilt. Okay, now what you do is you modify this in a 2 category problem. What you can do is you can modify this to an equivalent problem where for class number 2, which is this cross class, I just take the negative of each point. Okay, so which means I map, instead of this point I map it here, and instead of this point I map it here, just minus of that point. I do that for one of the classes, not both. And if I do that, it's exactly the same problem. I'm still looking for a hyperplane, but I want that hyperplane which is such that all the data points are on one side of it. Okay, if I find that hyperplane where all the data points of this modified data set are on one side of it, then on the original data set it would be passing between those two. Okay, the solution region is exactly the same. And in this way you say that I always want this to be greater than 0, never come less than 0. Okay, because that's the one side of a hyperplane. So yes, the smaller it is, the better it is. Ideally, I want it to come to 0. If this comes to 0 all over, then that means all the points are on one side, and that means all the points have been correctly classified on the modified data set. Okay, so this script y here is the modified data set where one class has been multiplied by -1. It's an equivalent problem. It's just an easy way to see it. Okay, you can think of it even without this modification, because the points on the positive side of the hyperplane will all be positive and the points on the negative side will be negative. So by multiplication with the -1, yeah, yani negative numbers added subtracted are the same as positive numbers on the other side, right? So you can think of it like that. But the only point that I want you to see here is that I can choose a cost function which is more conducive to gradient descent because it doesn't have the problem of 0 gradients. I can choose a cost function that allows me a margin here, a margin of B. Okay, because exactly this solution, the one given by the solid line here, exactly this solution is going to be exactly touching one of the points. Okay, the figure that I was making, I have to do that again. But you can kind of see in the same kind of figure, I have 2 points here and I have 2 points here. There are a lot of separating hyperplanes that I can draw. Okay, one of them is exactly this hyperplane. This hyperplane does give me 0 error, but it's not such a good hyperplane because it's too close to this point. Okay, and even this one is not such a good hyperplane because it's too close to this point. It might be a nice idea to choose a hyperplane somewhere in the middle. Okay, and that's the idea of margin. I say, okay, give me a hyperplane that separates them, but it is at least B away from each point. So this B is the notion of a margin. Okay. All right. So in fact, this idea is a simple idea, but this forms the basis of what are called support vector machines in machine learning. Very popular classifier. Before deep learning came about, this was the classifier of choice. Okay, I would say like 15 years of dominance in machine learning to this classifier. Okay, we saw this before in where we mentioned an SVM before very briefly in one of the lectures. Where was it? Which pictures? Rome wali mein, no, not really. In Hog, histogram of oriented gradients, we said we're gonna the original Dalal and Tricks paper also proposed this. They're going to find some features, the histogram of oriented gradient features, and then they're going to take they're going to pass them to a classifier, and the classifier they used was an SVM classifier. Okay, I will not go into the derivation of SVM because we really are going to skip it and jump to deep learning. But just the basic idea. If you have two data sets like this, which are linearly separable, you can draw this as a boundary. It's a valid boundary, zero error rate. You can draw this as a boundary. It's a valid boundary, zero error rate. But SVMs are tuned to find a boundary that maximizes the margin between the two data sets. Okay, so they and it's a neat, clean solution. I mean, you can solve this theoretically through a discrete optimization process. You will find a boundary which is maximally away from the nearby points of the two classes. Okay, so you try to maximize the margin, and people have seen that this type of boundary strategy of finding the boundary which is maximally away from your data points and still separates the data set actually generalizes very well. By generalization, what do we mean? When you will give me new points, will they be classified correctly? And people find that this strategy of doing a maximum margin classifier actually generalizes well to new data sets. And it kind of makes sense. Why would it generalize well? Well, because whatever samples you were given, you didn't draw a boundary too close to them so that a new sample which is a little bit close to them but falls on the other side will be misclassified. You try to, given your training set, you try to find the boundary which is maximally away from them and yet classifies them correctly. Okay, so that's the notion of a maximum margin classifier. It works very well. Here's another illustration. There are both these are B1 and B2 are boundaries which are giving me zero error rate here, linearly separating the data set. But B1 is better than B2 because the margin of B2, which means how far around B2 can I expand before I hit a data point. That's the notion of margin. So the margin of B2 is much less wider than the margin of B1. Okay. And so out of all the possible linearly separating hyperplanes that you could have drawn here, I mean, out of all the possible separating lines that you could have drawn here, you try to find one which has this maximum margin. Okay. That's the notion of maximum margin classifier. And I will skip this slide. We're kind of done. One last concept in linear classifiers. We talked about linear. What about nonlinear? Okay. What if the data is not linearly separable? The data is really not linearly separable.
What is meant by linearly separable?
Linearly separable means I can draw a hyperplane that perfectly splits the data into two classes and there is no error. That's a linearly separable data, like the figure that I drew before. Okay. What if the data is, okay, let me give you a picture of non-linearly separable data. What if it is like class number 1 is like this in my feature space, yani some very low feature values and very high feature values belong to class number 1 on this axis, and then class number 2 is really here. Okay. There is no like decent way for me to draw a line and get a reasonable error rate. Of course, I can't get a perfect error rate, but I can't even get a reasonable error rate on this problem. Okay. So the data is highly I mean, the data is, to be able to well separate this data, you need a nonlinear classifier. Okay, so this is kind of like I'm saying, okay, I focus so much on linear classifiers, but linear classifiers will apply only to maybe a few problems, not to every problem. Okay, yes, question. Okay, all right. So what we do is we have non-linearly separable data. Okay, but what we do is actually we map this data to a higher dimensional space to make it linearly separable. Now this is actually counterintuitive. because we generally don't want to map data to higher dimensional spaces. In fact, when data is in higher dimensional spaces, we want to come to lower dimensional spaces. We have this whole plethora of techniques of low dimensionality reduction available to us to map the data to lower dimensional spaces. We saw PCA, for example, as an example of that, and there are some other techniques also. We know that in higher dimensional spaces, we face the curse of dimensionality more and more. So it's not such a good idea to go to higher dimensional spaces in general. But in this case, it is maybe a good idea. Okay, there is a special need to go to higher dimensional spaces in certain cases, and that's this case. If the data is non-linearly separable, you will have to come up with a non-linear function to separate that data. But I'm saying it is possible that you map this data to some higher dimensional space, and then in that higher dimensional space, the data becomes linearly separable. Okay, and so what we do is we come up with a set of functions. These are called phi functions, where your feature vector x is mapped to y of x, where y of x are y1, y2, y d hat. These are some nonlinear functions of the original data. Okay, so I take my data from a d-dimensional space, I map it to a d hat dimensional space, where d hat is much higher than d typically. And if I do that properly, I can actually guarantee that no matter what type of data you give me, I can come up with a mapping of that data such that it will become linearly separable. That is kind of always possible. Okay, and I'll prove that to you that it's always possible. Okay, okay, let me prove that in just a moment. Okay, let me first go to the next slide. Okay, so the idea is that in a d hat dimensional space, I will have linear separability of these yix points, x points transformed by y. I will have linear separability of those. This is a linear separable kind of linear function. Okay, so in that space I will have a linear function, whereas in the original space there was no linear function that can separate my data. Okay, here's an example. Okay, so we took a very simple example, only we took a very simple example, only one-dimensional data. Okay, so one-dimensional data is not linearly separable if there is one class point and there are 2 points against it, around it. Okay, this is not linearly separable, because linear separability in one dimension is just a threshold. So data would have been linearly separable if I'm able to find a threshold where all the category 1 points are on this side and all category 2 points are on this side. It's a very simple example. So if I have a category 2 point on this side and this side, then this is not linearly separable in one dimension. Okay, so we took a one-dimensional example. I'm saying, let me come up with a mapping. What are my y functions, my psi functions, or my phi functions? What are those? They are 1, x, and x squared. The original data is x. I come up with functions 1, x, and x squared. Okay, what that really means is that g of x would be a transpose y, linearly separable from, let's say a is this, I have some weight vector, a is this. Okay, so g of x becomes minus 1 plus x plus 2x squared. So what will happen is that you will give me an x, this is x is equal to minus 1.2. So I'll plug in minus 1.2 here in this function of a parabola, because this is really a quadratic function, and maybe this 1.2 point maps here in that parabola. Okay, and then you give me some x close to 0, and maybe that maps here, and then you give me some point which is like 1.2 plus 1.2 of the other class, and maybe that point maps here. Okay, and now in that space, in the space of those possible parabolas that I could have drawn, but I chose one of them, in that space this data is linearly separable because this is one class and those are other classes. Okay, so I have a three-dimensional space now, whereas originally there was a one-dimensional space. Now I have a three-dimensional space, and in that it might be linearly separable. Okay, now why did I, so here's an illustration of that. I take this data and I map it to a curve like this, and then this is a separating hyperplane which can, it's a linear separating hyperplane which can separate between those two classes. Now why did I say I can always do this? Okay, let me give you the argument for that. Remember that figure we were trying to classify admission data? Okay, So we figured out that, let's say, this is a good boundary for third dimensional data. Okay, it's nonlinear. We figured out this is a good boundary. I can write this boundary as a polynomial of some order. Let me say this is a polynomial of order 4. Okay, if this boundary was more complicated, I would need a polynomial of order 10. But no matter what boundary you give me, I can write it as a polynomial. Even if the boundary you gave me was some sort of sinusoid or something complicated, I can take the Taylor series expansion and write it as a polynomial. Right? So I can always do that. Okay, so if I can write it as a polynomial, I will make those phi functions as 1, x, x square, x cubed, dot, 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 to whatever polynomial order you have. I will make that mapping. Okay, and then each data point is just linear weights on these polynomials. Right? Because a data point will map to this polynomial, it will have some coefficients. If you fix this polynomial, then those coefficients are nothing but linear weights. You can write it as A transpose Y, where those Y's are these polynomials. Because that's what a polynomial is. It's some constant times 1 plus some other constant times x plus some other constant times x square plus some other constant times x cubed. That's what a polynomial is, right? So if those polynomial functions get into y, then the weights are nothing but linear weights on those polynomials. And therefore, that's a proof. You give me no matter what complicated boundary, I can always push it into a higher dimensional space and separate it with a linear hyperplane, with a separating hyperplane in that higher dimensional space, always possible. Okay? And so summary, linear classifiers are not so trivial. We looked at a very restrictive case of classifiers, which are those classifiers that have linear discriminant functions. The discriminant function is a hyperplane. We looked at that specific category, but then we realized that this is not such a bad category. This category can generalize if you choose appropriate mapping into a higher dimensional space. Then this is actually a completely general solution to classifiers. Okay, and those who are familiar with SVMs, we apply a kernel function before we push into SVM. That kernel function is just a nonlinear mapping getting into your data. So those are called kernel SVMs. All right, any question? I feel much more happy that I have a pen in my hand while giving the lecture. Yes. No, I did not say that we can only find linear discriminant. I said let's look at the restrictive class of linear discriminant functions, right? So you're going to try the order of polynomial. You're going to say, I think a polynomial of order 6 would work well. It's a hyperparameter. You'll have to experiment with it, right? So you say, I think a polynomial of order 6 is good enough for this data. Well, no. And we always don't use polynomial functions. We use some other types of functions also for the nonlinear mapping. But I'm saying I've just proven that the polynomial can always do the job. It's just a proof that the linear separating strategy is not a bad strategy if I'm allowed to push into higher dimensional spaces. But remember, as you go into higher dimensional spaces, your coefficients that you have to learn keep increasing. And so the dimensionality problem is there. All right, any question? Okay, so let's come back to image classification because we have been just drawing these two-dimensional things. So here's an image classification problem from the CIFAR 10 dataset that I talked about before. There are 10 classes, 50,000 training images, each of 32 by 32 size. There are 10 labels. These are color images, so 32 by 32 by 3. There are 10 labels, and we have 10,000 test images. This is what the dataset looks like. Okay, we are going to apply linear classifiers to it. Okay, so what is a linear classifier? Well, I'll be given an image. I have a mapping fxw. W is what x is the original data. W is what I'm after. I want to find that out. Once I find that out, I'll have a linear mapping, and we are going to take the linear machine approach here. I'm going to learn 10 different classifiers, which means there are 10 mappings here. Okay, each one is going to give me one number, and then I'm going to see which number is highest, which classifier, which trained classifier gave me the highest response. Whichever is highest, I'm going to assign it to that class. Okay, this is a 3072 dimensional problem. I'm not doing any special feature engineering here. I'm not saying let me compute the SIFT features of this and use that for classification. In fact, what I'm doing in this formulation is I'm saying let me use all the pixels as a feature. So it's a 3072 dimensional feature, because that's 32 times 32, which is what 2 to the 1024 times 3. Yeah. Okay. So the 372. All right. So essentially what is happening in this problem is that each color value is a feature. Okay, and then I'm trying to distinguish between these 3000 dimensional feature vectors. I'm trying to distinguish between classes by finding a separating hyperplane in this 3072 dimensional space. Okay, and that's a problem because we know curse of dimensionality. This is a big curse. It's a 3000 dimensional feature vector. Yeah. Yeah, okay, good question. Why don't I just convert them to grayscale? I could, and I could say I mean, the choice of feature vector is in my control really, and I want to choose one which is good. Here, I didn't do any particular engineering here. I just said, let me choose the original. Whatever I'm seeing here, let me use that as a feature. Okay, but you are saying let's convert them to grayscale. Yes, I can do that, but then remember that it will come at a cost. For example, this ship category has a lot of blue in it because ships typically are in an ocean. So there is a lot of blue in it, and you will lose that distinction because you mapped into grayscale, and this blue is going to look pretty much like any other plain background of, let's say, the grass field here, for example. Okay, or the truck category has some fire trucks and they are red, so you will start to lose that type of information. If there is, so in general, what's the rule here? If there is some discriminability in features, you want to retain them. What I'm saying here is that there is some discriminability in color here, and so maybe I want to have some sort of color feature available with me. I didn't have to take this approach. I didn't have to say that, well, pixel values are the best features. In fact, before deep learning came about, nobody really ever took this approach because it wasn't a very successful approach. They instead went for gradients or gradient directions, hogs or SIFT or things like those. But I'm saying now I'm going to do something dumb. I'm just going to say, okay, let me forget about features. I'm just going to, the raw data that came to me, I'm going to use it as a feature and not do anything more intelligent than that. Okay, this is just an example that I'm giving you. Okay, so you have something concrete example in your mind rather than those two-dimensional figures that I was drawing. Okay, so what's my mapping? Because my mapping is linear, how do I use the weights? The weights just multiply with the vector to give me the value. Okay, so there is a set of weights for class 1 that I've learned. I will learn, I mean, through gradient descent or something. There's a set of weights for class 2. There is a set of weights for class 3. And how do I apply the weights? I just take this dot product. In fact, look at this. What is written here? This is entirely like what? Sorry. It's a dot product with each of the vectors. We have seen this before somewhere, where you multiply a matrix with a vector to map it into. Sorry. PCA. It's a change of basis in a sense. Okay, what's going to be the dimension of this W? Because I have 10 classes. So this W is going to be, I mean, the first row is the learned weights for category 1. The second, because this X is, what's the dimensionality of X, by the way? It's 3072, which means this number of columns in W must be 3072. Otherwise, matrix multiplication is not going to work. Okay, and how many rows? If I have one row here, I'll get the value for the first class. So I put a second row for the second class, I put a third row for the third class, and so how many classes do I have? I have 10. So W is going to be 10 by 3072. If I get that sort of a W, what is this essentially doing? if you think of it as a change of bases, it is transforming, linearly transforming, because it's a linear multiplication. It's linearly transforming. It's a change of bases which is linearly transforming your 3072 dimensional space into a 10-dimensional space. And in that 10-dimensional space, each category has a region. Whichever is the highest, I'll say that's the region of that category. Yes. Yes. Because that's what a linear classifier does, right? A linear classifier is, remember what we wrote, A transpose Y. So really what I have here in W is A1 transpose Y, A2 transpose Y, A3 transpose Y, where these A's are the weights. That's the linear machine strategy. Remember I said we'll learn G1X, G2X, G3X, and then just take the max of them when we want to classify something. So all of that is now contained in W. All right? I'm just giving this example so you have some concrete numbers in your mind of how that. So W is 10 by 3072, X is 30722 by 1, so F is 10 by 1. So once you have learned W, how will you learn W? Through gradient descent. I mean, some procedure, we'll talk about that. But once you learn W, you just multiply W with an X and then take the max. That's all you do. Okay, just to give some example numbers here. Here's a W, X. Remember we augmented X by 1 because we wanted the linear term. So here it's written separately just for you to be able to see it. Or I could augment X by 1 and then put this linear term also here because that will get multiplied by that 1. Okay, so these are the learned weights. How we learned them, I didn't show, but we somehow learned them. So what will happen is that you'll give me a column which represents the image. I have these learned weights of the categories. I'll just multiply them linearly, Wx plus B, okay? And then I'll get some numbers. And so I'll get a score for the first category, a score for the second category, and a score for the third category. And which one is the best score, depending on what my cost function was, whether high values were good or low values were good. I mean, depending on how I chose the cost function, which one is the best score that I will assign this image to. Okay, is that clear? So here I have 4 pixels and 3 classes. That's the example that we are giving you. What does this linear classifier do really? If I don't allow you to use any mathematical variable in your answer, I mean, just say in words, what is this linear classifier doing? Sorry? Recognize objects, yes, but how? What is it using? What is the distinction that it is creating?
So there is a possibility that the has the object close to the center or around the center, so it might be modifying boundaries by giving weights that are around the that are away from the center less value.
Yeah.
And then closer to the center more value, and then there is a
Yeah, yeah, kind of correct, right? Oops, sorry. So what is really going on is that there is a 3000